All right, so when we had a single spin, remember that we just had a two-dimensional Hilbert space, right? So if we had just a single spin, we had this up x, well, up z, down z, and that is sufficient to describe any state of the system. Okay, so I can describe my spin state as a linear combination of these two vectors. I could, of course, use an orthogonal, okay, an orthonormal basis. Remember what that is, okay? So if I just take this direction, square root of 2 up and square root of 2 down, that is what we are calling up x. And in fact, if you take a perpendicular to this, okay, that's the down x, right? So you can describe this, any vector, in terms of those two components, whatever components you want to choose. Okay, you can describe your general state vector in terms of either the eigenstates of Sz or Sx or Sy. Okay, so that's that. Now, that means if I just want to describe the state of the system, I have to form a linear combination of up and down for the system. Okay. Now, what happens if I have two spins? Well, first of all, if I have those two spins, the second spin also has independently an up and a down state, right? So I can say, if I want to describe this system now, I can say, well, the first system I can describe in terms of this up and down z eigenstates. The second state I can describe in terms of the up and down eigenstates of the second system, right? So if I just then look at the space in which I have to work, how many dimensional must it be? 4, right? In order to specify fully the behavior of this, well, I can, if I want to describe them independently, I can do something like this. Okay, so this will be our notation. What does this mean? This means a spin state.
Both particles are in states.
Okay, so this is for the first state. The one that I write first is going to be for the first electron. This is for the second electron. Okay, so you have 4 possibilities. Okay, up, down, down, up, and down, and down. So if I could draw a 4-dimensional space, I'll attempt it anyway. Okay, so this direction will be up, up, perhaps, up, down, okay, down, up, and somehow perpendicular to all 3 of them is a down, down, okay? So this is something like that. Okay, so there's this 4-dimensional space, and now I can describe my overall state as a linear combination of these things. Okay, so yes.
Doesn't this have some problems with indistinguishability?
Okay, we have said nothing yet. Okay, so about indistinguishability, these 2 particles may be different particles. Okay. So, okay, we'll get to indistinguishability. That's something else. Okay, so we have a set of space like that. Okay, now this construction is called the outer product state. Now we have seen inner products. Okay, inner products tend to reduce the dimension of the space, right? If we have an inner product, then what we get out of the inner product is a number. Here we have the outer product of these two spaces, okay? So there's this space and that space. Outer product means construct a space so that it covers all possibilities, okay? So I have all possibilities corresponding to the possibilities in these individual states. So you can sort of see what it is, okay? So this is all the possible cases of Z measurements in individual spaces, okay? Now, but I also know that I should be somehow able to construct these total spin states, okay? So I'll take just one of them, okay? So I'll just take this one at the top and try to find out what S squared up gives me, okay? Whether it gives me something like this, okay? And I'm also going to look at SZ up. Okay, so these are states of the system, but I don't know what it means in terms of the total angular momentum of the system, okay, total spin angular momentum. And so I want to figure this out. Now, this is actually easier, so let's just start with that. What is SZ operating on this? So what is this? This is SZ1 plus SZ2, right? Operating on up. So SZ1 is an operator that sees only the first particles. And SZ2 is an operator which sees only the second particle, okay? So this thing operates on that, and that thing operates on that, okay? So SZ1 hitting on that gives me what? Okay, so I know how those things go. Well, what about in this case? Okay, what's SC upspin? So, okay, it gives me H bar over 2 upspin, right? Because it's an eigenstate of that. Okay? So this operating on the first one, so let me just do it slowly. SZ1 up plus SZ2 up. But this SZ1 operates only on this. SZ2 operates only on the second one. For the SZ1, this thing is just like a constant. Okay, it doesn't operate on it. It is some other particle, right? So this gives me H bar over 2 up. This up is still there. Plus, okay, this up. But then I have this one, which is again up, but H bar over 2. And I get H bar up. So what does that mean? Okay, this is an eigenstate of SZ with m value equal to what? 1, right? Because it gives you 1 H bar. Okay, but that doesn't mean that it is an eigenstate of this form, SMS type of thing. Okay, so to check that, we have to do some bit of algebra. Okay, so we have to look at what S squared, okay, multiplied by this thing is. So S squared up equals what? Okay, well, let's see. What is Okay, so let me do it the same way that we did earlier. Let me just look at what s squared is. In fact, let me just look at s plus or minus. Okay, so let me just take, okay, where do I want to do the algebra? Maybe on a new board. All right, so all right, let's see what s plus s minus is. Okay? So this is going to be equal to sx plus I sy times sx minus I sy. Okay, you'll remember that we did this earlier, but I'm just going through it so that we refresh our memories. So we have sx squared plus sy squared plus I, okay, sy sx minus sx sy. Okay, so this is going to be, this piece I'm going to write as s squared minus sz squared. Okay, so it's almost s squared, but it's missing an sz squared. Okay, and then I have plus I, commutator of sy with sx, so it's in the wrong direction. So it's going to generate a minus sign, minus I h bar sz. So this will be s squared minus sz squared, okay, plus h bar sz. Right? Please check my algebra so that I don't make minus, plus or minus errors. Okay, so in fact what I'm after is the s squared term. S squared is going to be s plus s minus plus sz squared minus h bar sz. Okay, so this is what I was after, because with these things I can manipulate my terms much more easily rather than working with sx, sy, etc. Okay, so let's now see what s squared up is. Okay, so this will be some amount of messy algebra, so please help me out. So it's going to be s plus s minus plus sz squared minus h bar sz operating on up. Okay, but now we know what sz operating on that is, because we calculated that over there, right? So what do I have? I'm going to get the first term, which we have to work out, s plus s minus, okay? And up, plus, what is sz squared operating on that?
H bar squared.
Okay, h bar squared and up, right? What about this one?
Minus h bar squared. Since there's the factor of h bar there as well.
Okay, so this sz operating on that, remember, was h bar times the same thing. So I have another h bar there, so it's going to minus h bar squared up. So that's very nice. These two terms cancel. So I still have to calculate this s plus s minus business, right? And for that, I have no other choice but to expand it. Okay, so s plus, remember, is s 1 x, okay, plus, okay, perhaps I'll do it slowly. Okay, so this is now going to be sx plus I. No, I don't want to do it that way. I want the pluses and minuses. Okay, so this is going to give me S1 plus S2 plus, right? And then I have S1 minus plus S2 minus. Okay, so I just write this thing as first and second particle, first and second particle, and it hits on up, up. Okay, now I really need help. Okay, so first of all, let's see. I have this thing which will operate on that, right? And that one will operate on that, right? The first, the one with index 1 operates on that, the one with that operates on that. You remember what the S plus and S minus operating on these things are, okay? Well, S plus operating on this is what? 0. What about S minus operating on that?
Down.
Down. What's the prefactor?
Square root of L plus.
Okay, so what's that?
L square root of 1 over 2 times 3 over 4 minus minus 1 over 2 times 1 over 2 times minus 1 over 2, 3 over 4 plus 1 over 4, 1.
1. Very good. So that's one thing that I can remember very well. Okay, this is down. So S plus on down is also just up. For spin 1/2 cases, S minus on down is what? 0, okay, because there's no place to go down. Okay, so I have these things. So now I'll do my algebra. Okay, so this piece here is just S1 plus S2 plus. Okay, and then there will be 2 terms. This one operates only on that one, so it's going to be up, down. This one operates on only that one, so it's going to be down.
Isn't that the other way around? First one operates on the first one. S1.
Yeah, first one operates on first one.
It is my down. Okay.
This one, okay? So I have that. Now I have to go back and work this out. Now this thing up can operate only on the first object and it's down. This can operate only on the second object and only when it's down. Okay? The other one, for example, S2 plus acting on this one is going to give me 0, right? Because there's no place to go up. Okay, so now if I do that, okay, I already forgot a factor h bar here. Okay, because there's this h bar factor, wherever it is, over there. Okay, so there's that h bar factor. Now this will also bring an h bar factor, so it will be h bar squared. This will convert this to up, up. That will convert that one to up, up. So I'm going to get 2 up, ups. So what happened? I have h bar squared, okay, 1 times 1 plus 1, up, up. So this is an eigenstate of the s squared operator. Very nice. I found an eigenstate of the total spin operator. What is the value of s? 1, right? Because it gives me 1, s, and s plus 1 is 1. Okay, so this says to me that 1 up, up is really equal to, it's equal to 1, 1. It corresponds to total angular momentum equal to 1, z component equal to 1. In fact, the z component is easy to check because the z operator just picks out the z components of each one of them. So it's h bar over 2 plus h bar over 2, so it's going to be 1. So that's easy. The s squared part is not the so easy part. Okay, so, but in any case, we found this. Okay, so that's very good, because now that we have this, we can lower this and find what 1, 0 is and what 1 minus 1 is. Okay, so let's just do it. Yes?
I couldn't understand why did we apply the S1 plus on the first term.
S1 plus, okay, this one,
Yes.
okay, will operate only on this one because it's a raising operator. So it's looking for something to raise.
So the other
Okay?
one will give 0.
Yeah, this one will give 0. Same thing over here, okay? S2 plus is looking for the second spin, okay, which needs to go up. So it will not be able to raise this one, but it will raise that one. Okay, okay, any questions? All right, now we come to the more interesting part. What are all the other stuff? So what we are doing here is that we had this outer product state, okay? The outer product states which give us these 4 directions in this space, and we either can express spin states in terms of these or the total angular momentum states. Okay, so we are constructing these outer product states for the total angular momentum state. So what we are finding the relation between them. All right, so here we go. We just noticed that s squared 1, 1, okay, is s squared up, up, which gave us h bar squared times 2 up, up, okay? So that's our 1, 1 state. Now, if I operate with an S minus on the 1, 0 state, 1, 1 state, sorry, what will I get? Lowering operator. Which one does it lower?
1, 0.
Okay, so it lowers the Z, okay, index, which is MS. So this is going to be 1, 0, but there will be a prefactor. Okay, square root of, let's just check. Yes, okay, so 1 lower, okay, so MS minus, yes, okay, so it's going to be, there's an H bar and a square root of 2. So that's what I get. But I can also operate on this stuff here. So I can look at S minus up, up, right? So this is the same thing. So I can, instead of 1, 1, I can operate on this. So this is going to be S1 minus plus S2 minus operating on up, up. What do I get? This one is trying to lower the first one, which it can do. This one is trying to lower that one, which it can do. So what do I get?
Up, down, up, plus up, down.
Yes, okay, so I'm going to get up. The factors are 1, down, plus down, up. So one of them lowers the first object, the other one lowers the other object. So now just looking at, okay, I again forgot my H bars. Okay, H bar. So now if I look at this line and that line, okay, what do I get? I get 1, 0 is equal to 1 over square root of 2 up, down, plus down, up. Okay. So that's another one. Okay, so maybe I'll just write these things down and put them in boxes. So 1, 1 is just up and up. 1, 0 is this guy. Okay, so I can do this, play this game one more time, right? To get 1 minus 1. Sure.
How did we operate S minus 1, 1, 1 and end up with 1, 0?
Okay, just look over here. Just look at the expression at the very bottom here. Okay, S minus operating on S ms is going to give me this factor, which in this case is square root of 2 times H bar.
Then how 1, 1 corresponds to up, up?
Okay, that is because if we go over here, we found out that, okay, in fact, it's over here, S squared operating on 1, 1, we went through this algebra and found out that this quantity here, up, up, is an eigenstate of S squared with the correct eigenvalue, okay, which corresponds to S equals 1. Remember that this term here is S times S plus 1. So for S equal to 1, I should get 2. Okay? So I get the correct eigenvalue for S squared. And I also have the correct eigenvalue for SZ, wherever that is. Okay? Somewhere on the board over here, we have SC operating on that. Yes?
When we went through this algebra, we already knew that the S was 1. We're just trying to find the MS, right?
No, we didn't really know actually very much, right? We just operated on S squared. Okay, we operated on up, up with S squared and tried to find out if it's an eigenvector.
But the total spin is 1.
How do we know?
Is it 1 over 2, 1 over 2?
Yeah, but you don't just add things like that. Okay, so we don't just add the spins of the two particles and say that that's the total spin. Okay, we have to make sure that this object here is an eigenstate of S squared. And whatever comes out of it, and it turns out that what came out of it is H bar squared times 2, tells us that this is S equal to 1. Okay, it's not guaranteed that if you have two spin 1/2 particles, that their total spin will be 1. In fact, we'll see an example here where it isn't. Okay, so that's that. Let's also look at S minus 1, 0. What will that be? Let me not forget the H bar. What will this be proportional to? I'm going to lower ms, so it's going to be proportional to 1 minus 1. What about the factor? Okay, ms is 0, so that goes away. S plus 1, so it's going to be square root of 2, right? So square root of 2. Okay, but let's also operate on this, which is the 1, 0 object. So that's going to be 1 over square root of 2 up, down, plus down, up. Okay. Now S minus. So this is going to be S1 minus plus S2 minus, operating on 1 over square root of 2 up, down, minus, down, plus, down, up. Okay. So S1 minus can only operate on this, because otherwise it will give me 0. S2 minus can operate only on the second term. Okay, otherwise I'm going to get 0. So what do I get? I get, okay, there's going to be an H bar again, which I shouldn't forget. Well, not here. Okay, there will be an H bar over root 2, but there will be 2 terms which are going to give me down and down. Okay, and you see now if I just compare this line with that line, what do I see? 1 minus 1 is equal to down, down, which makes sense, right? If the 1, 1 state is up, up like this, right, then 1 minus 1 state is going to be down, down. So now, yes.
In above case, we had 4-dimensional space, right?
Yes.
But in 1, 1, it is 2-dimensional, right?
In 1, it's 3-dimensional.
No, okay. So you see, what we are trying to do, okay, I erased my funny figure here, but I have this 4-dimensional space, okay, made up of up, up, down, down, up, and finally a fourth one down, down. So the Hilbert space for 2 spins together is a 4-dimensional space, right? Because single spin is 2-dimensional. We just find the outer product of that with another 2-dimensional space, so we have a 4-dimensional space. Now, what we are doing here is we are generating an alternative set of eigenvectors. So if I now draw those things, try to draw those things on the board here, okay, so this up, up is also equal to 1, 1. This down, down, we just figured out, was equal to 1 minus 1, okay? 1, 0 is a linear combination of these other guys, okay, so there's some sort of 1, 0 over here, but we are not done. Okay, because we need, again, 4 vectors to span this space. Okay? So what do you think will the 4th vector be?
Up, down, minus, down, up.
Okay, so just looking at the symmetry of these things, we know that whatever we are going to find has to be orthogonal to all 3 of these things. Okay, so now we are trying to find out a 4th one, which is going to be orthogonal to this, orthogonal to that, and orthogonal to that. And I'll just tell you, as your friend suggested, the result. Okay, it turns out that it's a 0, 0 state. Let me write it at a separate place because this is somewhat different. Okay, so 0, 0. What does that mean? Total angular momentum is 0. And also, since the total angular momentum is 0, the z component of the spin is going to be 0. There's no other way. Okay, so this is going to be 1 over root 2, okay, up, down, minus, down, up. Now, how did I do that? By just making sure that it will be orthogonal to all of these things, but obviously you have to verify this, okay? You shouldn't trust me. And so, as an exercise, let me put exercise here. Maybe I'll convert this into a homework or something. Okay. Okay. So what is find s squared 0, 0, and find sz 0, 0. Okay. So just verify that what I am saying is correct. Okay, so these things now have names. You see, I also found another object here, which is going to be 0, 0. So these are, again, 4 orthogonal vectors which span this space, and they are useful for certain purposes. Okay, so we would like to use these total angular momentum states for 2 objects, for 2 spins. All right, the 3 objects here, which correspond to s equal to 1. Okay, so these are called the s equal to 1 triplet, because there are 3 of them. Okay, so that's the total angular momentum equal to 1 state. This one over here, which is alone, is the s equal to 0 singlet. Okay, because there's just one such state. Okay, so the spin states of 2 spin 1/2 particles are made up of the total angular momentum states which form a triplet of s equal to 1 and a singlet of s equal to 0. Okay. Now, why did we go through this stuff and find out these things? Because we could have worked out in the outer product state, right? We could have worked the outer product state and we wouldn't have to worry about how the what the total angular momentum is and such things. Well, let me just discuss with you a case which we'll discuss in more detail on Monday. Okay, so suppose I have a system, okay, which has these 2 electrons, okay, and these 2 electrons are inside the system, perhaps an atom, and then this whole thing has some amount of total angular momentum. Okay, so its total angular momentum is made up of these 2 electrons plus the angular momenta corresponding to perhaps orbital motion and everything. And then at a certain time, we find out that it just releases 2 electrons. So one electron goes this way, the other electron goes that way. And we look at the change in the angular momentum of this atom. And we find out that the change in the angular momentum of the atom is 0. What does that mean? From angular momentum conservation, the total angular momentum of these 2 electrons is 0. Okay? So that means, okay, so the total, let me just write this out in English, total angular momentum of these 2 objects is equal to 0. That means it must be in the singlet state. Okay? So that means that the wave function corresponding to these 2 electrons is going to be 1 over square root of 2 up, down, minus down, up. Okay? Yes?
We could have also predicted this with the Pauli exclusion principle.
We have not discussed such things, okay? We are going formally, okay? We are going step by step, okay. So we have something like this. Now, you see this is the state of the first electron. That is the state of the second electron. That is the state of the first electron. That is the state of the second electron. So it's a superposition of these 2 states. Okay? Now, I can make, okay, so I'll call this one the first electron and this one the second electron, or the electron going left and electron going right, okay, instead of calling it first and second. So if I measure, say, the z component of the, okay, so now I make a measurement here of sz. And I find out that it's plus h bar over 2. What does that mean?
The other electron's wave function will collapse to minus h bar over 2.
Yes, okay, so it means that I have measured this bit. Okay, so it had 50-50 probability that first one is up and second one was down. And this is the second one is up and the first one is down. So I have these 2 probabilities, they are 50-50. But when I measure that the spin of this one is plus h bar over 2, that means my wave function has collapsed into this piece. Then I know definitely that the electron on the other side has downspin. Okay? So, yes.
Also for 1, 0 case, 1 minus 1 case, we derive these from lowering and lowering operators. How can we derive, intuitively I can understand, how can we derive 0, 0 case? Because there is no...
Okay, it's not simple. So what the simplest way is to take my definition as a challenge and operate on it with s squared and sz and verify that it is indeed the 0, 0 state, okay? So I have not derived it, but I just told you the answer. And the way that you do this usually is by looking at the orthogonality among these functions. You are looking for something which is orthogonal to all 3 of these things. So what you can do is you can take the most general case. You are going to have A plus B up, down, plus C down, up, plus D down, down. And just find the inner product of this at the first object, second object, third object, and find out what relation these things must have.
Definitely we can, by your way, we can find the left right side, but how can we find out that it's equal to 0, 0 state?
How can I find that zero? I can verify it. Okay, that's how I'm verifying it. If I look at, if I operate on it with s squared, and if I get, okay, 0 times the same thing, okay, with an eigenvalue of 0, so that piece is okay. And if I operate on it with sz, and if I get 0, then I'm okay. Okay? All right, so how are we doing on time? Okay, a few minutes. Okay, so what we have demonstrated here is that a measurement of the spin on the left-hand side will give you a definite information about the spin on the right-hand side, okay? So these two spins, these two objects are now called entangled. So entanglement is an important feature of quantum mechanics, which says that if I now make a measurement on the left-hand side, somehow we'll see I can influence the measurement on the right-hand side, okay? So I can use this, not perhaps alone, but along with other methodology which involves classical methods of transferring information. I can just combine them together to transfer information from one side to the other side. Okay, so this is what's called quantum information. So this entanglement opens a whole, okay, wide spectrum of applications. So on Monday, I want to go into as many of them as possible. Okay, so I'll see you Monday.